Thank you. Take it away.
All right. Well, thank you all for being here. Before I start, I guess, okay, I have an echo, so that's not an issue. Before I start, I guess let me mention that I'm like traditionally mostly a mathematician, and I work in a math institute, and this is actually my first computer science conference. And I'm very excited to be here and listen to all these computer science talks. I hope still my talk makes somewhat sense, although maybe a lot of you have a different background from me. So this talk, John worked with Benedikt Ahrens and Paige who are not here, and Niels, who just gave the talk right before me. And the aim is to understand, well, univalent double categories. And there's in some sense like a three-point aspect to this talk. So let me give you like an overview that should not make sense, but hopefully at the end of the talk it will make sense. So let's see. And so the first aim is some kind of, let's say, meta-mathematical or meta kind of scientific principle that there's a deep connection between univalent foundations and categorical structures. And in order to understand kind of categorical structures up to interesting invariances, it's beneficial to look at them kind of from a univalent perspective. So this is kind of the thing that I want to convey first in the first part of the talk. Then I want to kind of apply this perspective to a really interesting particular example, namely double categories, getting to the title of the talk, and look at how one would formalize double categories. And hopefully at the end, I will also mention somewhat how, okay, if you actually want to manage all the data that a double category has, which we will see, and in this part, we want to use two-sided displayed categories, which is kind of like well, we just saw displayed categories, and this should be like a related notion that can help us manage the data of a double category. Okay, but let's start at the basics. So what's math? And I will not be able to answer this question in full generality. However, I think one thing that we can agree on is that math is very good at kind of looking at interesting objects and finding kind of unifying principles, right? So we look at various operations and extract a monoid, or we look at various kind of spatial properties and extract this notion of a topology. And by now we have a lot of different mathematical objects. So what we want is a mathematics for mathematics, i.e. like some kind of unifying principle for different mathematical objects. And what is the principle for that? Well, I think a good one is compositionality, right? So a lot of common mathematical objects have some notion of assignment or mapping or morphism, whatever you want to call it. And they're usually composed unitarily and associatively, right? And that's precisely captured as a notion of a category. A category is kind of more or less that, right? It's an object's morphisms, and those morphisms compose in a nice way. And so in some sense, we can think of category theory then as a mathematics of mathematics. So now one concrete benefit of this approach is that categories give us a notion of sameness, right? So axiomatically, in some sense, we can define two objects to be same if they're isomorphic in the category. And there's a technical definition for this. There's two morphisms in both directions that compose to the identity. And instantiating this in concrete examples gives us very familiar notions. So if you're an algebraist, you will get like isomorphisms of algebraic objects. If you're a topologist, you get homeomorphisms. If you're a set theorist, you get bijections, and so on. And so one question is, okay, what happens if I apply this to categories themselves? So I can define the notion of a category of categories, where the objects are, well, functors, so the generalization of functions to the categorical setting. And what we get from this is the notion of an isomorphism of categories. So it's exactly like a bijection of objects, a bijection of morphisms that kind of respects the structure in the appropriate setting. However, it turns out this is not the only notion of invariance that category theorists care about, right? So category theorists often like to look at categories up to a more general notion of equivalence. So if you know what this is, great. If not, there's a definition. If it doesn't tell you anything, don't worry. The only key aspect of it is that it's a weaker notion than isomorphism. And here's an example of the kind of properties that we can look at for a category. So if you have two categories that are isomorphic, they will have the same number of objects, so to speak. But in general, equivalent categories will not. On the other hand, there are a lot of like key categorical properties. So like the last couple items, like existence of colimits or local presentability, whatever they mean, they're like very kind of important categorical properties that category theorists like to study. And they are actually invariant on equivalence. We don't need isomorphisms. This is like it's too strong as a condition. So you kind of in a situation where you have one object, but that one object has two reasonable invariances, and you care about both, depending on what you're trying to do. So that's kind of inconvenient. If you're like, sometimes you have to be like more specific about what notion of category you're kind of looking at. Like, is it category up to isomorphism or equivalence? And there's this kind of abstract kind of categorical setup with some cool numberings that do make sense, but I will not explain. And you can talk about like 1-1 categories, and that means up to isomorphism for some reason. And there's 2-1 category, that means up to equivalence. But clearly it's not ideal because you then always have to specify, I have a category in, let's say, the 1-2-1 category, or the category in the 1-1 category. So unless I specify, I don't know what the context is. All right, so up to here, you might say, so what? There's one notion that has two invariances, and one is strictly stronger, so who cares? Just make one standardized decision to pick the weaker one, and if you really need to, specify that you need the stronger one or something. But of course, you can see where this is going. Like with all of science and computer science and everything else, things get complicated really fast. And it turns out categories can be generalized to a more general notion, namely double categories. So this slide is well-timed. So a double category comes up if we don't want to just axiomatize an object with one type of morphism, but with two types. So there's actually a long list of relevant examples, kind of coming from set theory, algebra, up to computer science, where really like the two morphisms and their interplay is really what we care about. And so there's this abstract generalization of a category which makes that precise. That there's an actual definition of a double category which builds on objects, two morphisms, and many, many axioms. And because the structure is more complicated, as one might expect, there's way, way, way more notions of invariances. This is just a select list. This is not exhaustive. And you can find this list by Googling for like an hour or so. It's really not that hard. Like there's various papers studying double categories in various settings, and every one of them might use any of these notions for whatever reason because they focus on a different aspect of double category theory. And notice also, these are not strictly included in each other. Like, it's not true that one implies, like, there's a post set of relations between those. Some of them are not comparable, and so on. So it gets very chaotic very fast. So that's definitely not a convenient situation. Like, we have this web of invariances for our double categories. And yeah, so then we have to always keep track of what we're talking about. So let's summarize the situation. We have a challenge, namely, we have this interesting mathematical notion that appears in nature that can be studied up to various levels of sameness, depending on what we are trying to do. One solution that is kind of common in classical mathematics is to like really be precise and always state, okay, this property holds up to, I don't know, vertical biequivalence, this one up to gregarious equivalence, and so on. And the principle that we kind of aim for, that comes from this work, is that instead of working in classical setting, working in some sort of univalent setting, you kind of like change the invariance from the context into the object itself. And you can kind of like define your objects in a way so that it incorporates its invariance as part of its structure. So that's how we're going to get to. Okay, so here I will make a transition to formalization. You all know what formalization is, so this is just like a fun slide. So like if you didn't know what was happening, this one will be very clear. The only really important point I want to make is that in the last like 2 days, we have seen many formalization talks with many different proof assistants like Lean, Coq, Agda, and so on. And for our setting, beyond just dependent types and functional extensionality and stuff like that, we really, really need the univalence axiom, right? So the univalence axiom, if it's added to a type theory, gives a very rich notion of identity types, gives intentional identity types, and this is like a key property that we need to be able to kind of incorporate our desired invariances. So we work in the set of Coq unimath. Presumably, if you work with other univalent proof assistants, you could also do that, but something like Lean would not work for this right now, because you really need univalence. Okay, so let me go back to the category theory example, because double categories are really long. So I can actually tell you what a category is, more or less, right? So you can like just using simple dependent type theory, sigma types, pi types. There's no magic and no trick. You can just sit down and write out the definition of a category. The only thing that I want to point out here is that there's like this. I don't know if you can see the pointer, but like, I don't know. Hope it's clear. The last line, there's this proposition that says is a set. And that is because what we want to specify, in order to get what we think of as a category, we need to have the property that actually the identities of morphisms are really just a property rather than a structure. Like two morphisms are either equal or not, but there's nothing deeper happening. So we add this proposition. This would not be necessary if we were working in some extensional type theory, but we need this as an extra condition to make sense of what a category is. So now the claim is we take this definition of a category, so objects, morphisms, plus the axioms, and we add one property, and then it will have exactly the right invariance that we wanted. And this has already been done actually quite a while ago. This goes back to work by Ahrens, Kapurkin, and Lamstein, who show that we can, for example, impose the condition that the objects also form a set, and then, in some sense, everything reduces back to the non-univalent, non-homotopical setting, and everything is isomorphism invariant. And more kind of non-trivially, there's this kind of univalence condition. So this is like a little bit of wordplay. So this is a univalent category is not literally the same as univalence in the type theory. It's a proposition that we impose on the category, and it implies that it has this nice equivalence invariance. So if we take the type of univalent categories, then it is exactly true that the identities of those correspond to equivalences of categories, like when we look at it from an external perspective. And notice this has like meaningful like implications. For example, I can define now a kind of assignment from these set categories just to sets, which takes like the underlying objects. This makes sense, right? I mean, how would I do this? I take my objects and I take the witness that my object is a set. That is exactly an assignment that takes my category to the set of objects. I cannot do this for univalent categories. Like, Calc will not let me define the set of objects of a univalent category in general, because it will not form a set. It's not an equivalence invariant notion, so the proof of system will not even accept it. Okay, so for categories, this is basically it. So it's not like as deep as one might think. But of course, our major aim here is to focus on double categories, which are like, well, much more non-trivial. So I will not give you a full formalization of double categories, because that will take me like hours, and you will get very bored very fast. So let me just give you an overview of the kind of structures you encounter in double category theory. So you have, again, objects. You have two types of morphisms. You have squares between the morphisms, and then you have an ocean of identities, composition, unitality, and associativity, which can be strict or non-strict, weak. Everything is possible. I think a more instructive picture is this, where like the relation between them is better captured as identity types. So you have objects, then you have horizontal and vertical morphisms that depend on the objects, and so on. And so giving you this picture, if you have like enough experience with dependent types, you can just sit down and formalize this, right? This is like not hardcore deep a priori, when you just sit down and put these all together. But turns out it's somewhat more subtle than the textbook definition of double categories would suggest. So let's see what kind of challenges we encounter. When you try to formalize double categories from a textbook definition, like in a so-called unfolded sense, you often encounter such equalities, right? So you have this equality where I have a square, and I want to compose it with a different square, where the other one, the top and bottom are identities by assumption. And like the textbook will say, this should be equal to the square where the top and bottom remains the same. This is just written in the textbook. And now what you could do is you could say, all right, I just defined this in Calc, and I say, okay, take a term in this thing. And then Calc will yell at you. And why will it yell at you? Because when you compose the left side, you don't actually get f. You literally get f composed with the identity. And f composed with the identity is equal. There's a term somewhere that tells me that they're equal, but it's not like literally equal. So you have to do a lot of transports. So what ends up happening is you get like this like simple identity. It's like you have to like add lots of like stuff there. So for example, there's this operator here, like this boundary square transport that you have to like say, okay, I have a square, and then I have like this, I transport along a bunch of identities. And this is true for every single identity you have. Like whenever you have a bunch of things working with squares, you have to then think about, okay, which additional identities I have to add and which transports I have to do so that the proof assistance will actually accept it as a valid identity in this setting. So this becomes like, it's possible, but it becomes tedious very quickly. And so what we want is a more folded approach instead of the unfolded approach. And for that, we use a kind of appropriate generalization of displayed categories. So we already saw displayed categories. There was a very nice detailed discussion with very nice follow-up questions. So I don't have to say too much about this anymore, but exactly a displayed category is in some sense trying to define, you start with some category that you care about, and you impose kind of like dependent types over the objects and morphisms, which we think of as the original object and the original function plus additional structures, whatever. The stereotypical example is groups, for example, but yeah, we saw, for example, the example of what monoidal categories and so on. What we want to do is think, okay, how can we think of a double category as a structure over something? And the way we want to think about it is that in a double category, we have, going back here, so if you just restrict to the, let's say, the first column, this just looks like a category. So we have this as object O, we have verb being like the morphisms and the composition. And so now the rest of this seems to be some structure on top of this category. So what we want to do then is to like think of, define this notion of two-sided display category, where we have one category given by objects and vertical morphisms, and then we have this additional structure of a category coming on top of this. That depends on like two kind of like the category times itself, essentially. And so this is like a very elegant approach because it kind of separates the task of studying a double category into first the category and then all of the structure on top of it. And it allows for like a lot of like simplifications in the way we like formalize things. And concretely, we can reuse a bunch of like existing code from like category and two-category theory. For example, if you want to study a univalence principle, we just have the univalence of the underlying category, and then we look at the univalence of the fibers. And it also helps constructing examples, because if I have already an existing category in the library, I can already start with this. All you have to do is to specify the fibers and the interactions. So it cuts down on like how much formalization I have to do to get new examples. Let me make a note that there's also additional examples if you're super into hardcore category theory. There's like, you can think of a two-sided displayed category as a good way to study two-sided vibrations. So this is like a little bit for the category theory nerds in the audience. All right. How am I doing on time? Oh, cool, great. Yeah, so in my last minutes, let me now go back to, in some sense, my second slide, I think. So now this slide should make sense, and I can explain a little bit more detail. So what we did is first, we provided this method of translating, in some sense, like between formalizing categorical structures and desired invariances. So, and the interesting thing is that, so that in the translation at the top, it says provides appropriately weak definitions. And what's happening is that sometimes when you want to choose the right invariance, you need to kind of add appropriate kind of like associators or uniters and so on. And this is exactly where like the category theory literature can be super useful and like telling you, okay, what kind of coherences you want to look for. That maybe if you just want to try on your own in the proof assistant might be really tricky. So there's this nice kind of feedback loop between those two notions where you get exactly categories up to whatever invariance you want. And yeah, I don't know. We looked at the concrete example of double categories. And so there's this fun thing where like now we have to come up with words essentially for all these like double categories we get that are now defined up to chosen invariances, but it didn't exist in the literature. So now you can say, for example, a double set category is essentially just a double category, but defined to be up to isomorphism. Whereas, for example, we have like, I don't know, univalents to do double categories, which are invariant under horizontal equivalences or something. And this is just a sample. You get way more. But I guess at some point you run out of space on the slide, so 4 seems like a reasonable number. And finally, we did introduce as part of the work the kind of the technology of two-sided displayed categories as a way to like manage the formalization, kind of be able to kind of formalize things in a way that is meaningful. And yeah, maybe there's also kind of other applications, depending on who is interested in this kind of stuff. All right, so let me then summarize and like some future steps. We kind of discussed how we can use formalization in Calc Unimath to like manage categorical structures, focusing on double categories. Most of the double category formalization is kind of done, and hopefully in upcoming work we kind of finish this story and like give like this well-rounded account of most of what already existed in the literature. So the main kind of example being left is this notion of a double bicategory, which is like weak in all possible directions. And so this is hopefully done soon. And sure, and we hope that this can also lead to other examples applying to other kind of categorical structures, maybe even like higher like categorical structures, like so 3 or 4 categories, or maybe like other like monoidal or symmetric monoidal structures or something like this. And with that, I thank you. And if you have questions, I'm happy to answer.
Okay, thank you very much. Are there any questions?
Thanks for the nice talk. Yeah, I don't know, maybe it's more appropriate to talk about this offline, but I mean, if you define the double categories as like just then the two-sided displayed categories, but don't you then enforce already that, I mean, you have an underlying category, so your objects are always set? No?
Yeah.
Or?
Objects are not always set. Why are they always set? You know, even in a category, the objects are not always set. Right? Like if you have a univalent category, your objects can be one types, you know?
Yes, but I mean, so you start with a category, and in a sense, you put another category on top of it that you relate. So don't you automatically have some kind of strictness conditions?
So in this, yes. So in this, what you get is, this approach, what you get is that this one direction will be strict. This is correct, and so that's what I mentioned. So in this last slide, in what we're doing in upcoming work is to kind of look at like doubly weak double categories, which are like weak in all directions, and we cannot like literally just use the code we used. We have to like kind of reformulate things. But yeah, this one is like strict in one direction at least, and non-strict in the other.
Hello, so say I wanted to apply these fun methods, let's say displayed category, and something that's not univalent, like lean. How far would I get before I hit a wall and begin, crying blood or something?
I don't know, actually. I mean, presumably you could use it, but I don't know what issues would come up. Maybe you have a better take on this? I don't use lean too much, so I cannot tell you exactly what issues.
I guess it might only affect like the univalent part. That you might not look at like univalent stuff, but I think lean should have proper support for dependent type, right? Or
No. This is. I mean, this part would be the same. So I mean, I guess what the question is like, what will you do with it? Like if you want to formalize in groups in lean using this, I don't see any issues. But like the point of this is that you would not get like the nice equivalence invariance notion that you want. Because everything would be like literally equal, right? Like.
I was actually more interested in the displayed category thing.
No, but but displayed of what structure? Is it like if you displayed but like groups, then it's fine. But if you want displayed, I don't know, groupoids, for example. Usually groupoids, you look at equivalence of groupoids, not isomorphisms. So there in lean, I think you would have to issue that you have to like kind of, like it would not give you equivalence of groupoids by default. So it really depends on what mathematical object you look at, not the displayed part itself.
No, that makes sense. I just suffered greatly trying to formalize comonoids, so that spoke to me.
This is so set is commalized and say, that should. I don't see a priori an issue why it should not work. Yeah.
Are there any more questions? I have one. So yeah, you've got this kind of asymmetry where you start with some category and then you build the other one. So like you start with the horizontal one, I think, and you put the vertical one on top.
Oh,
I mean, even in the, and he said like it's asymmetric already because one of them's strict and one of them isn't. But even if they're both strict, what happens if you, let's say you're working with someone else's stuff and they've done it the wrong way around?
yeah.
And how is there an easy way of translating back and forth between the two?
Well, if they're strict in both directions, then you can flip things and nothing would change. But this is true. I mean, this is like in the literature, it is true.
When they've proved all their theorems one way around and you want it the other way around. I mean, they've made one, like you want to transpose the entire double category. Just swap the horizontal and vertical.
Yeah, I mean, if both sides are strict, you can always flip this, right?
I mean, is that an easy thing to do with your formalization?
Sure. Like I said, if it's strict in both directions, then yes. But if it's not strict, then it's not true. So.
Oh yeah.
Yeah. But this is in general true in the literature. It's funny because, like, depending on which textbook you look at, they do have different conventions. So when you start formalizing, you have this like inconsistency you have to deal with, which is like not. Yeah, this is exactly also like maybe like a random selling point for the formalization aspect. Is that maybe you could more standardize this. I don't know. Like fix one direction and stick with it throughout.
More questions? Well, thank you again.